So now for the paper 2 stuff. First question's about chromatography. You've got a brown ink that it's asking you a little bit about. It's asking you to investigate chromatography with the brown ink, and you've got to answer some questions about chromatography. Now, chromatography is a very simple process. You've all done it since year 7. Be interested to know that single dyes would give a single spot, and mixtures would give you multiple different spots. So each of these is going to be a single spot. This one's going to be a mixture of them. And I'll just remind you as well, the chromatography, we use a special sort of paper, chromatography paper, and we call that the stationary phase because it doesn't move. And we also use a solvent, usually water, but we can use ethanol or other solvents as well. We call it the mobile phase because that moves through the chemicals that you're investigating through the paper. So it picks them up, carries them around. And if you've got very soluble compounds, you get very high movement, you get what we call high RF. And if you've got very insoluble substances, they stay down near the bottom. Right, but you've got some mistakes on here you have to identify. There's a number of possible mistakes here. The first of which is that the solvent line, which is here, should be below the start line. So solvent above the start line, and if you have the solvent above the start line, and that can cause a bother, and what would happen is all of the inks you've got here, the inks would dissolve in the solvent or the tank water, and you wouldn't get any chromatography taking place. And then second answer, or second issue, the most common one you'll give probably, is that you're supposed to use a pencil line. So the mistake is that the line is drawn in ink, start line drawn in ink, and the issue there, of course, is that the ink will mix with the colours you're trying to investigate. Ink will mix with the solvent and be carried up the page and make a right old mess as well, wouldn't it? Right, so that's no good. You should also, or you could also as an alternative, doesn't really matter if you use water as a solvent. If you're using any other solvent, you need to make sure you've got a lid, otherwise all the solvent evaporates. So that's the third possible way of getting the mark there. That's that one. And here we go, we've got the chromatography done. As you can see, as I proposed earlier on, the red and blue and green will give 3 spots. The green one is insoluble, the blue one's very soluble, and the yellow and red are somewhere in between. And the brown ink's looks like it's got all 4 inks used to make that dye. All 4 colours used to make that ink, I should say. Right, 2 conclusions that the student can make. So brown ink contains all 4 colours. Sorry, not all 4 colours. Contains red, yellow and blue. It's not all of them, is it? Red, yellow and blue spots or colours. There's also an extra one there. We don't know what it is yet. So there's an unknown colour or unknown dye in there as well. There's other things you could have got for the mark though. So for example, there's no green ink, otherwise there'd be a spot down here, wouldn't there? No green colour. And as I already mentioned about the solubility, that's the most soluble and that's the least soluble. I guess you could have mentioned that. Or that one's got the lowest RF, that one's got the highest RF. Any of those things could have got you marks as well. Right, why was the green still at the start line? And the simple reason is that it's insoluble. So things that don't move up the paper are insoluble, so that would have stayed there at the bottom because, well, for the reason I've already explained, so I'll move on. And then you have to work out using the RF, you have to work out the distance it moved. So this is using the RF calculation but in a slightly different way. So let's just fill in. I think most of you prefer to fill in the equations rather than rearrange first, but the thing we need to work out is the distance the solvent moved. So we need to work out this thing using this equation. So we know the RF, as given to us in the question, is 0.24. It is equal to the distance moved by the colour, which was 1.8, so I should have written that above, shouldn't I? Divided by distance moved by the solvent. So that's the thing we're trying to work out. So 0.24 is equal to that divided by that. You've got a mark even for just setting it out, just literally filling in. So even if you're stuck and you're no good at, you're not great at rearranging equations or something, simply fill in the numbers to this. So in other words, equals 0.24 is equal to 1.8 divided by that down there. Okay, I'll write it again. Then hopefully you can rearrange. And so the distance moved by spot, or distance moved by solvent, is equal to 1.8 divided by 0.24. You get a mark for just figuring that out. So it's 7.5 centimetres. So this is simply a rearrangement. So the distance moved by solvent I put up the top there, and the 0.24 I put down the bottom there. And if you want help with that, chat to your teacher, chat to your maths teacher, or whatever. Happy to go through that with you, but I'm not going to really spend time now rearranging. Let's move on to question 2 instead. And this is all about water safe to drink. So potable water, or potable as it's sometimes pronounced, potable, water that's safe to drink. Compare how potable water can be made from either sewage water, fresh water, and by the way, for your course you need to know how it's made from seawater as well, which by the way, just as an aside, is desalination, removal of salt, desalination. You can do that by 2 methods: distillation or reverse osmosis, right? And that's the other way of doing it that this question is not about, and that requires loads of energy and stuff, doesn't it? But we here have got to compare groundwater and wastewater. Now I'm not going to sit and write this out, I'm actually going to put the mark scheme in front of you and just walk you through it. So the mark scheme is set out as a table. I would encourage you to set it out almost in a table like this. There's nothing wrong with that at all, because you're really, what they call the indicative content, the facts you're expected to know are all set out in this table. Ideally, you'd make it really clear what the differences are and what the magnitude, the size of the similarities as well. But setting it out as a table is absolutely fine here. Okay, so groundwater, this is rivers and reservoirs. This is water that we get, in Kent we get our water, I think, from reservoirs and whatnot. And it's fresh water, it's very easy to obtain. And you should know the sequence of steps used to obtain groundwater. So this idea of just screening to remove the insoluble bits, and then essentially then sterilisation using chlorine or ozone or UV light. That's obviously very quick. So some details here about how you would do it. So the filtration through the filter beds, and the idea is to remove the insoluble particles. So that could be grit or sticks or even fish, I suppose. And there's fewer steps, and so I'd probably make a note if I was doing it. There's fewer steps than producing waste or producing water from wastewater. But as I said already, you have to sterilise it, and there's a bunch of different ways of sterilising it. And the purpose of that is to kill pathogens that might be bad for you, to kill bacteria. The wastewater could be factory water, it could be sewage water. Clearly much more difficult to obtain, more processes and takes more time. The first step is the same, but just like the triple exam, you have to kind of know the other processes. So sedimentation, just leaving it to sit for a while. And what happens when sedimentation takes place is the organic matter, this is sewage water now, all the organic matter they call it, in other words the pooey stuff, right? So poo or organic matter stays down there, that's what we call the sludge. Great name, sludge. And up here we've got the effluent. Up here. You're expected to know then what you do with the sludge and the effluent. But for this particular question, it's asking about the water, so you don't get any marks in this question about saying what's happened to the sludge, but they treat that anaerobically or via anaerobic digestion using bacteria. Okay, anaerobic digestion of that, but that's a bit of an aside. But the effluent, you need to know that you treat it using aerobic bacterial treatment or aerobic biological treatment, and that makes it safe to put back in the rivers, but then you'd have to sterilize it using chlorine, you know, the same as before, to kill the final bacteria. And you do get marks mentioning the sludge is anaerobically digested. Okay, so there we are. So that's the way that one was set out. There's quite a lot going on in that question. I think that was pretty hard to get all the marks there, so well done if you got that one. I'm just going to skip on though the rest of question 2, which is all about producing potable water from salty water. I've already told you this, haven't I? I should have read the paper before doing this, shouldn't I? And you simply have to say that you use distillation, as the other alternative is reverse osmosis. And a little calculation to finish off with, another concentration calculation. But remember, the concentration in grams per decimeter cubed is equal to the mass divided by the volume in decimeters cubed, mass in grams. In this case, that's 2.4 grams divided by the volume. Now I've got it in decimeters cubed here, so you get a mark for converting to decimeters cubed, which is 0.150. Right? There's 1,000 centimeters cubed in a decimeter cubed. So to get from there to there, you divide by 1,000. To get from there to there, I've divided by 1,000. And that comes to 16. The way that the marking worked, you get a mark for converting to 0.15. You get a mark for setting out this equation, and you get a mark for the number. There are other approaches to get you there as well, but this is probably the easiest way. Okay, I'll stop there.